Okay, so here in Chapter 5, we sort of have the bridge that connects basic probability to inferential statistics, what we'll be able to do there. And in Chapter 4, we talked about discrete and continuous random variables, and we focused more on the discrete random variables, and binomial random variable is an example. But with a continuous random variable, which is what any variable that follows this normal distribution is going to look like, is one of the biggest applications that we see of probability and inferential statistics. So we've seen this normal curve before. We talked about this back in Chapter 2, and we talked about the empirical rule, or the 68, 95, 99.7 rule. So we're going to really be doing the same thing we were doing with those 68, 95, 99.7 rule types of problems, but we can be more specific. And I'm going to lean on the calculator for this. Your textbook authors will show you how to look up these values in a table in the back of the book. You're welcome to try that if you like. I can show you what that looks like here, but in the long run, it's going to be much easier to use technology for these. So in a normal distribution, it has these properties that we've seen before. The mean and median and mode are all equal. It has that bell shape to it. And what we want to consider is that the total area under the curve is 1, or it's 100%, because generally what we're talking about is the proportion of values, or proportion of observations that we would see in particular intervals. And as inferential statisticians, it allows us to ultimately make decisions as to whether things are unusual, or if a claim is not likely to be true. So the points that we talked about before, if I go 1 standard deviation below to 1 above, that's 68% of all of the data. In the normal distribution, if I go 2 above to 2 below, that's 95%, and then 3 below to 3 above, 99.7. So, but what if I go 1.5 standard deviations, or what if it's not an even z-score that I'm looking at? Okay, we're going to be able to deal with that. So here you have a few different normal distributions. A couple of them have the same mean, right? In A and B, we have the same mean at 3.5. They have the same center, but the difference is the spread. The standard deviation in B is much smaller. And then in C, we can see the standard deviation is the same as B, but the center is different. The center is at 1.5 instead of 3.5. So we want to think about always the center, the shape, and the spread of a distribution, but all normal distributions are going to have that bell-shaped curve. So which curve has the greater mean here? Obviously curve A, right? He's centered around 15, and B looks to be centered around 12. Which curve has the greater standard deviation? That would be B. It's wider. There's more variability in B than there is in A. Okay. So if here we just want to do our best to estimate, and a lot of times I kind of go with the Goldilocks principle to answer a question like this. But I can see that the center is somewhere between. You can see that the center is somewhere between 280 and 330, and we could just find the midpoint of that. And then we're going to approximate the standard deviation based on that 68, 95, 99.7 rule. So we can see the mean would be right around 305, and then if we said 50 was the standard deviation, that's probably a little too high, right? If we go up to 355 on that scale, that's probably and 50 in the other direction to 265 or 255 rather. It's probably more than 68%. So again, a little bit of that is just the eye test, but we're using that 68%, 95%, 99.7% because we expect that to be true. Okay, so now in a standard normal distribution, we've seen this before, we calculated z-scores back in Chapter 2. If your z-score is 0, it means that your raw score was equal to the mean, right? We calculate a z-score by finding the raw score minus the mean, and then we divide by standard deviation. So a z-score of a 1 means that you're 1 standard deviation above the mean. Okay, so in the standard normal distribution, we're going to now go a little bit beyond what we've done before, right? What's the cumulative area? Like if you're at a z-score of 0, you're at the 50th percentile, okay? We want to start to make these a little bit more complicated. So the cumulative area that corresponds to a z-score of 1.15, let me show you what I mean by that. We are saying here, if my z-score is 1.15, what's the cumulative area? So 0 lives here, 1.15 would be over here. If it was really simple, like 1, well, we would know that would be the 84th percentile, where we could at least approximate it. But 1.15, that's going to be a little bit harder. So I want to show you a feature on your calculator. I'm going to just write the syntax first, but we're going to look at this shaded area. And what I need to do is come up with a lower limit of the shaded area and an upper limit. So really, in truth, my lower limit is negative infinity. But if your calculator doesn't allow you to put that in there, you can just put something really big like negative 1,000. Okay, but that area to the left continues to go on. So what we tell the calculator, just like in the last chapter we had binomial CDF, there is a normal CDF, but this one's actually easier to use. And we would put in our lower limit, we would put in the upper limit, and then we enter the mean and the standard deviation. So what are our lower limit and upper limit here? Well, we have negative 1,000, or just some really big number, or negative infinity. The upper limit, this stops at 1.15, and it's a standard normal distribution, so the mean is 0 and the standard deviation is 1. So on the calculator, what does that look like? We're going to use the same menu that we used before. Most of the time in this class we're in stats, but for a couple chapters here we use second vars, the distribution key. And here you're going to see the normal PDF, we never use that, so don't ever pick it. Go right to number 2, normal CDF. And look, they do allow me to put in negative infinity there. It starts off with that. My upper limit is 1.15. And again, don't panic if you don't get a screen that is set up like this. I'll show you what you ought to do. So if your screen just looks like this, normal CDF, again, don't panic if you don't know how to find that negative 1e to the 99. Just put a big number, a big negative number in there, right? How about negative 1,000? That should work. Okay, and I find that it's 0.8749. So what your textbook authors are going to show you here is that we can look that up. We can go to this Z table in the back of our book and look up 1.1 and then find the second decimal, which would be 5, 1.15, and the area to the left is 0.8749. Well, where this gets a little bit more complicated is when we have to find an area that's not directly to the left. So the cumulative area that would correspond to negative 0.24, right, would be 0.4052. That's that blue area there, right? Or we could use our calculator, normal CDF, negative 1,000, or a really big number. That's our lower limit, upper limit, mean, and standard deviation. So I prefer to use the calculator, okay, where I think the calculator is much better tool for us. Is when we want to find areas between two scores. So if I wanted the area between these two scores here, negative 0.75 and 1.23, normal CDF, we would go from negative 0.75 to 1.23, 0 and 1. And I don't have to look anything up on a table. I just get that area right away directly without having to dig through a table and subtract values. See, they're going to find 0.8907, 0.2266, and then subtract the two of them to get 0.664, which we got right away. So we get 0.664 right away with the calculator. No need to subtract 4-digit decimals. Okay, so what happens when we want an area to the right, right, above 1.06? This gets even more confusing with the table of values, right? What we're looking at now is 1.06. So if we're trying to use our table of values here, if we look up 1.06, we're going to get the wrong answer. We're going to get this white area here that we don't want. We could get this by looking up negative 1.06, but again, that confuses people. Or we look up 1.06 here, we get the white area, and we subtract it from 1. Or we can just use our calculator, second enter. We'll back up a little bit here. My lower limit now is going to be 1.06. So my lower limit now is 1.06, and what's my upper limit? Something really big. How about 1,000? Mean 0, standard deviation 1. Oops. Oh, I want a 1 there. 1,000. All my commas are okay. So I get 0.14457. Okay, so when we look up 1.06, we don't get the number we want, or we use normal CDF and look it up that way. And now in the second part of Chapter 5, what if our mean's not 0 and 1, our mean and standard deviation are not 0 and 1? Not a problem, right? Suppose I want to answer something like this. Well, we still do the same thing we just did. Lower limit and upper limit, mean and standard deviation. We just want to be a little bit more careful about our lower limits. Like negative 1,000 might not be big enough if my mean is 500, we're dealing big numbers. Now, it really is going to depend on the standard deviation. The standard deviation here is 100. So once I go 300 or 400 below 500, I'm really far from that. So our negative 1,000 or negative 10,000 is still always going to work in those cases. But watch out for the standard deviation. You know, if you're using a number like negative 100 as your lower limit on the z distribution, that's fine. But if the standard deviation is bigger, we have to be careful of that. So what would this look like on our calculator? Lower limit, we could make that negative 1,000 or negative 10,000. Upper limit is 600. Mean and standard deviation are 500 and 100 respectively. So I have normal CDF again, it's cut off here. Lower limit negative 1,000, upper limit 600, and then we enter our mean and standard deviation, and I get 0.8413. Again, you're going to see a lot more work to be done if we follow your textbook authors. First, they're going to convert these to z-scores, okay? And then they're going to use those z-scores to find that area that exists under the normal curve, but we can find it right away with our calculator, okay? So let's take a look at this example here. We'll skip the z-score calculation and just use the calculator. A national study found that college students with jobs worked an average of 22 hours per week, so that's going to live in the middle of our normal curve, with a standard deviation of 9. A college student with a job is selected at random. Find the probability that the student works for less than 4 hours per week. So that's going to be really, really unlikely if the average is 22 hours a week, but let's draw that and try to picture what that looks like. So 22 is going to live at the middle of this normal distribution, right? The average college student works for 22 hours a week. We want to find the probability somebody works for less than 4. And remember that the standard deviation, they told us, was 9. So this is just going to be normal CDF. Go like negative 100 or 1,000, if you want to use the same number every time. Up to 4, that's my upper limit. The mean is now 22, and the standard deviation is 9. So the only difference with the second part of Chapter 5 is the mean and standard deviation won't always be 0 and 1. It's the only difference. We're doing the same thing with our normal CDF calculations. That's the only extra piece to that. Now your textbook authors do a little bit more work. They found the z-score of negative 2, and they looked that up on the table. We just used normal CDF. So just a quick overview of Chapter 5. 5.3 I'm going to look at now, finding values. And then 5.4 I sort of give it its own little section. That is the central limit theorem, and I'd rather sort of separate that. So I'll do a separate lecture on just the central limit theorem. And then 5.5 we will skip. So here we have 5.3 where we're finding values. So these questions are going to feel a little bit different. Okay, what does this look like? Find the z-score that corresponds to a cumulative area of 0.3632. So the question is now different. They're saying, what is the z-score so that the area under here is 0.3632. So the difference, what we were doing previously in the previous two sections, is finding that area. Now we're saying, well, what would z be? So I know the z-score is going to have to be negative. It's the 36 percentile roughly. So we go to the same place that we've been going on our calculator. This is called inverse norm. And the syntax for inverse norm works this way. This will work out nicely for us because it gives us an area to the left. We tell the calculator the area to the left of the score that we're looking for, basically the percentile, and then we enter the mean and the standard deviation. So for this particular example, the mean and standard deviation are 0 and 1. So this would just be inverse norm. We're going to tell the calculator that we want the z-score that has an area to the left of 0.3632, where a mean is 0 and a standard deviation is 1. So I hit second vars again, right? Second variable's key, and notice there's inverse norm. It's right there. Not hard for us to find. So I showed you the syntax already. If your screen doesn't look like this, just enter it in that order, and we will find our area to the left. You're going to see your textbook authors will, and just like we suspected, it was a negative z-score, negative 0.35. Your textbook authors have to do a little bit more work here. They are going to search the table for 0.3632, or the number that's closest to it. This can be a really difficult Easter egg hunt sometimes, so it's much easier, in my opinion, to use inverse norm. Okay, so notice what we have now, again, is find the z-score, but this is a little bit different. 10.75% is the area to the right. Let's think about this now, right? We have 10.75% is the area to the right of this z-score. So first thing I'm going to do, so I'm looking for a z-score that's over here that has a pretty high percentile, right? And they're giving me this, let's change 10.75% to 0.1075 first. So when I talk to the calculator here, I need to tell it the correct area to the left. So we're going to do inverse norm, but I'm not going to put in 0.1075. What I'm going to put in is 1 minus. Okay, so I'm going to put in 0.8925. So our area to the left of this z-score is truly 0.8925. This is 0.8925, right? The area to the right is 0.1075. The total area under the curve, remember, always adds up to 1. So we have inverse norm again. And this time we have 0.8925. So they tell me it's a z-score of 1.24. Again, your textbook authors are going to have to do a little bit more digging using the table of values rather than the calculator like we would do. So again, the first thing they did is the same though. They have to go get that 0.8925 because the table is going to be areas to the left, but they get the same number we got, 1.24. So maybe you already guessed where we would go with our next problem. What happens when the mean and standard deviation are not 0 and 1? We did this in the last chapter. We'll do it again. So the Peace Officer Standards training tests are normally distributed with a mean of 50 and a standard deviation 10. They will only hire applicants with scores in the top 10%. So let's think about what we're looking for here. We know that the mean is 50, but we want to know what should you score so that you would be in that top 10%. So we have to inverse norm 0.9. Mean is 50, and I need to peek back at the standard deviation 10. Okay, so we're going to inverse norm 0.9 with 50 and 10. Takes up even less space. So we get right away, they would need a 62.8, or we'd probably round that and say they would need a 63 score. Let's see how your textbook authors do this. They're going to go look up 0.9, find it, and they find a z-score of 1.28. But now they got to turn that z-score back into a raw score, and they get 62.8. I think it's a lot faster just to use that inverse norm feature.